So let's take a look at our processor in Logisim. So in one of the previous lessons, we built in labs, we built arithmetic logic unit. So let's go inside. So this is the old version of arithmetic logic unit that previous semester kids had to make. But then I realized it's really complicated, you see. So we divided it in two parts, in arithmetic unit and logic unit. So it's, easier to digest with the mind. But generally, there is this operation selector with which we select which arithmetic or logic action we want to perform. So either adding, subtracting, or calculating the negative number or whatever with this arithmetic part, or shifting bits, rotating left and right through carry, and or XOR not, and so on. So this is our arithmetic logic unit. We take also two numbers as inputs, A and B, and it just calculates the output Q based on the operation selection. And this thing also gives us some flags, signed overflow, negative, 0, and carry. And it takes in the previous values of these flags. So here's our arithmetic logic unit. And we also talked about general purpose registers, which is the memory in which all of those numbers are stored between actions. So our general purpose register block consists of, for example, in our case, of 8 registers. So Intel processors have 4 or 5 registers. ARM Cortex microcontrollers have, for example, 16 registers. Arduino processors have 32 of them. And so we have some control signals with which we can select which registers to put on data A and B outputs using these select signals. We can also select to which register to store the result. Here is the input of the result, data W. It's like data for writing. And these are data that are read. And we also enable writing or disable writing, and we have some clock signal. So in this Logisim, we can also hover the mouse over each of the inputs and see what's written there. So first signal is address for writing. We have 8 registers, so we need a 3-bit select signal, which I will call the same, data write address, which selects in which of the registers should we store the result. So for example, in this data write input, if I select 110, it is number 3. So whatever comes to be written in this general purpose register block, it will be written only to register number 3. All other registers are disabled, they will not be written to. Next input is address of A. So with this select signal, we select which register's content should be forwarded to A output. So it will be, I'll just copy it. It will be the same 3-bit select signal. I'll just change the name to data A. And I connect it to data address A. Oh, sorry, maybe I rather change the name to address A. And this will not be data for writing, it's address for writing. So address select, that's better name. And here I can also select address B. So which register to forward to output B from this general purpose register block. Okay, so I copy it, I change the name to address B, and with this signal, I will select address for B. Next, and we actually can Okay, we will not check it out yet. So we have other signals for general purpose registers, one of which is write enable. So when this input is low, nothing changes in general purpose register. You can switch all of these signals on or off, but nothing really changes. It's like a protection bit, write protection bit, so that, you know, when we do some other stuff in our microcontroller, these register contents are not overwritten. So it's a control signal. So write enable GPR, write enable for general purpose register block. So it's 0, so no writing is performed. Next input is clock. Clock. Okay, I'll just call it clocks, right? So, and here's the deal. In microcontrollers, there is this convention that, you know, to organize them in some way so that, you know, things don't go on and off randomly all the time, there is this convention that the clock signal, you know, changes from low to high and then back from high to low and so on. For example, in Intel processors at 2.4 gigahertz, this clock is switching on and off at 2.4 gigahertz. And the convention is that when clock goes from low to high, all inputs are read. And when the clock goes from high to low, all the results are written to the corresponding places. So in this case, clock basically will just control the writing of the result into the general purpose register block. So, but in order, so normally this general purpose register expects that when the clock goes from low to high, information is written. So we need to add a NAND gate in between so that clock signal is inverted. So it's facing east and it's located right here. So, and its data bits is just one data bit. So when clock goes from low to high, nothing is written because we read the inputs at that moment from flash memory or from data memory. And when clock goes from high to low, then this inverted signal goes from low to high and data is written to the registers. And the last input is reset. So when you turn on the computer, there is a circuit which sets reset high for a short period of time. So all the information in registers is reset to just zeros. So, you know, there's no old values inside. So I'll call it reset. There is this convention that all of the information that is inside the registers is reset to 0 when the processor is booted or started up. So these are the control signals for our general purpose register. Here is also the output A, and it falls right into the A input of our arithmetic logic unit. So I just connect them directly. And here is input B of arithmetic logic unit, and I put them in the same place as the output of general purpose register for easy connection. So here data goes from registers into arithmetic logic unit. And here at the bottom, the result of arithmetic logic unit falls out. I don't know, for example, A plus B or A minus B or A and B, the result goes out. And the result, well, we calculate it so that we can store it somewhere. And it's just written back to one of the selected general purpose registers. So this input is data to write into the registers, and with address writing input, we select in which of the 8 registers the result will be written. We switch on enable writing, we do clock high and low, and the result is written into the registers, in the corresponding register. And for arithmetic logic unit, there's also one input and one output. And this is the status registers flags. So to store for example, the carry bit between instructions, we need to save it somewhere. And for that, we will just put one small 4-bit register next to arithmetic logic unit, and we will call it status register. And it's just the same way, way built as these general purpose registers. It's just one separate register inside the CPU. So I go to memory, registers, I place it, and since we only have 4 flags, 0, carry, signed overflow, and negative, I select that I want this thing only to have 4 bits. And I will name it status register. So this is where data goes out, and this is where data goes from status register into the arithmetic logic unit. So I connect it like this. So, and this status register, it has several inputs, one of which is enable. You know, for example, if it's 0, status register is disabled. So right now, for the sake of simplicity, we will have it enabled all the time. So I select wiring. Data bit is 1 and its output value is just 1. So, you know, it's just enabled, whatever, it's just switched on. And it also has a clock input. And again, as I said, on rising edge, we read the inputs, and on falling edge, we write the inputs into the memory. So here again, the clock is taken as the inverted value of CPU clock, because CPU clock goes up, we want this thing go down, and when this clock goes down, this thing goes up, and the memory's values are updated. Because these blocks are made in such a way that they expect rising edge for writing, but for clock, we want it to happen on falling edge, so we need to invert this clock signal. And another input is also clear input, reset input. So, you know, I'll just connect it also to reset. So when we reset the microcontroller, the general purpose registers are reset to zeros, and also the status register is reset to 0, so there's no some old random data inside. And arithmetic logic unit has the final input, which is operation selector. So we can switch between adding, subtraction, copying, and logical operations, and it's done with this input operation select. And if you did the labs, you know that we have 8 mathematical functions and 8 logical functions. In total is 16 functions. So we need 4 bits to switch between 16 combinations. So I put a control signal here. I select number of bits is 4. I name it ALU op cell, arithmetic logic unit operation selection control signal, and I connect it here to arithmetic logic unit operation signal input. So what we have done here is the following. I can basically control this thing as a small calculator where I can add or subtract numbers or do any kind of things, and we will now simulate it. So let's go to general purpose register. So first, to do some math on some numbers, we first need to write the numbers inside general purpose register. Right now, I'll do it manually, but later as we build our processor, the values will be taken from either random access memory or from flash memory. But at the moment, since we haven't built it yet, I'm just going to manually write some values inside these registers. So let's say we have somehow magically got that register R0 contains value, for example, 5, register R1 contains value 4, register R2 contains value, for example, FF. These are in hexadecimal. And for example, R3 contains value 69, whatever, in hex. So, so registers have some values. And let's say I want to add the register number 0 and register number 1, and I want to store the result in register number 4. So written in a notepad, I say that I want, for example, to calculate register R4 is equal to register R1, R0 plus register R1. Let's say I want to do this thing. Okay, so the result should be 9. But let's try to do it. So looking at our notepad, here, this. So like this. So I want the result to be written into register R4. So for this address write input, I select register number 4. So it's 100. I click on this line and it says that this signal is equal to 4. And so if I go into general purpose register inside, it's hard to see, but address for writing is set to number 4. So register number 4 write is tied to enable writing. So, whoops, I will be able to write into register number 4. So next, for number A, we want to select register 0. So address A is just 000. So for register B, I want to select register number 1. So I just select this as 1. So address A is 0, address B is 1. And now these selectors are already outputting at A and B values at register 0 and 1. So when I click on this line, it says 5. So register R0 is already coming out here. Its value is already coming out through this cable, through this bus wire. And on the B, we have 4 because address is selected for that. So for example, if I select register number 3 and I click here, it says 105. So this 69 is 105 and that is forwarded. So I don't want that. I want register R0 plus R1. So address B is just 1 and it outputs 4. And now I need to select the correct operation. I want to add 2 numbers, and for that we need to remember how we build this arithmetic logic unit, but I summarized the functionality in this table. And when we built this arithmetic logic unit, we ordered the instructions in this order. So instruction number 0, operation number 0 is add. If we select 1, it will be add with carry. If we select 2, it will increment by 1, dec will decrement by 1, and so on. So in our simple example, we want to add 2 numbers. So I take a look in this documentation. It says to add, the selected bit should be 0. So it's 0. And if I click on this arithmetic logic unit output, it is already outputting the result 9. Okay, so 9 is already going to general purpose registers. But nothing is updating yet, because first of all, we need to turn on this safety switch to enable writing to the registers. So write enable for general purpose registers, and the result will only be written into the general purpose register number 4 when we have clock going up and then going down. So right now, if I click on this general purpose register block, register R4 is empty, 0, 0, nothing's happening. So input is already 9, but it's not being written anywhere. That's the reason why we have these latching registers. They need clock signal to change their values. If you disable the clock, you make sure that the registers are not being overwritten. So I click clock once, it goes high. The value is still not updated, but when clock goes from high to low, then the result is written to register R4. And so we have, basically, we just did this R4 equals R0 plus R1. Okay. Let's do another one. Let's say that, for example, we want to increment the value of our register number, for example, number 5 or number 3 plus 1. So we want to do this R3 equals R3 plus 1, which is just function increment R3. So how can we do that? You know, we can just go through all of these inputs and just connect them, set them correspondingly. So since we want the result to be written into register R3, this write signal needs to be set to number 3. So I set it to number 3. So the result, whatever will come out, will be written to register number 3. Next, for A, I also select register number 3 because I want to increment it by 1. So I select register number 3. Increment function only uses A as input and B is not being used. So I can select any register, doesn't matter, because only register which is selected by signal A will be used. So for B, I don't know, I'll just leave it all zeros, for example. That doesn't matter. I want to enable writing, so I leave this write enable general purpose register switched on. I want to select operation to int, and increment operation is operation number 2 for our processor. So I select 2. We can already check out what we have as inputs and outputs. So for A, the signal is this 105 or 69 in hexadecimal. So it's 105. And the output is already 106 because this thing is not clocked, or it's just simply analog, you know, in some way analog circuit. So it just calculates the output all the time. And it outputs 106. And now, you know, for this value to be written to general purpose register, I need to do a clock going up and going down. And now when I go to general purpose register, I see that register R3 changed from 6-9 to 6-8 because this is hexadecimal number. So after 9 in hexadecimal system, you have 8 is 10. Okay, so this is how this processor is performing some arithmetics, and this is how the results are written. So I see that somebody raised a hand. So maybe you can ask your question either by voice or in a chat box if you want. So, yeah.
Sir, can you hear me?
Yes.
I didn't understand. Can you repeat, please, why the clock is inverted, and what's the use for the status register in on the right of the analog of the arithmetic logic unit?
Okay. So 2 questions. First question. Also, so first question is about clock, why it is inverted. Well, if we build these registers ourselves, we would build them in such way that falling edge updates. the contents of the register. But because we used the logisim built-in memory registers, these registers are just built by this program in such way that rising edge of the clock updates the contents of the register, right? But because in processor world, there is agreement that falling edge should update the registers, then we need to put this inverter before our general clock so that this signal is inverted. So when the processor's clock goes from high to low, then this logisim memory cell receives from low to high and updates its value. So, if we built these memory blocks ourselves, we would have built them in such a way that falling edge is updating the content. But because we use the ready built-in library memory cells, which only update when the clock is going from low to high, then we need to invert the signal. This is just technicality,
Okay.
And the second question is about the status register. So in most cases, the programmer doesn't even use status register, okay? So, we wanted to increment a number by 1, we just did it. We wanted to add 2 numbers, we just did it. We didn't really need to use the status register. But now, let's say that we are using 8-bit processor, but we want to add 2 16-bit numbers. So how can we do it? Let's say this is a big thing. So no, yeah. So let's say that we want to do operations on 2 16-bit numbers. Let's say that these numbers are 0, 1, 1, 0, 1, 0, 0, 1. Okay, like this. Oh, and this is just 8 bits. I need another 8 bits. So 1, 1, 0, 0, 1, 0, 1, like this. So this will be our number 1. So it's 13,541. The question is, how do we store this number in our memory? And in reality, all microcontrollers that I know of, their compilers are built in such way that they store numbers in so-called little endian format, which basically means that if the number is bigger than the memory cell, you would use multiple memory cells, and the lowest memory cell will have the bottom part of the number, and the higher memory cell will contain upper part of the number. So let's say we want to add numbers 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, which is equal to 13,541, which is equal to 0x 34E5. So to store this number, since we have 8-bit processor, we need 2 registers. And let's say we are going to store in the following way. R0 is the bottom part, this E5, and R1 is equal to this top part, 34, 0x34. Okay, so there's just no way around it, This is how, for example, Intel processors are 64-bit today, but if we want to add 228-bit numbers, then in the Intel processor, the same thing will happen. Bottom part is stored in one register, and the top part is usually stored in the next register. So this is one of the numbers. And the other number is, for example, I need to select numbers such that the example works good. So let's say the other number is 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1111, for example. I don't know, like this. So this number equals to, I'll try to input it here, 0 1 1 0 0 1 0 1 1 0 0 1 1 1 1 1 1, like this. And this number is 26,015 equals to, in hexadecimal, 0x659f. So let's say we have to add them together for some reason, right? Uh, the second number also takes up 2 register memory cells. And let's say we are just going to store them in R2 is the bottom part, since we're using a little endian. Big endian just means that these are swapped. So top part would be at lower address and lower part would be at higher address. Network uses big endian and microcontrollers use little endian, and computers often use big endian for some historic reasons. So it's hard. You need to kind of check which endian you are using in the documentation somewhere. So R2 is the bottom part, 0x9f, and register number R3 will contain the top part, 0x65, like this. And let's say we need to calculate, for example, how much is first number plus second number, and we want to store the result in a third pair of registers. So we want to store the result in register pair R5, R4. So this is how it's written. The notation is top part, column, middle part, column, next middle part, column, next middle part, column, and the bottom part. In this case, we have just top part and bottom part. So register pair R5, R4 equals to register pair R1, R0 plus register pair R3, R2. Let's say we need to calculate it because, you know, there's no other way we can do it really. So we need to add two 16-bit numbers. Each of them takes 2 bytes, 2 memory addresses, and we need to add them. How do we do it? So, you know, just simple. We first add the bottom parts, and then we add top parts, right? So first action is R4 equals R0 plus R2. And the second action is R5 equals to R1 plus R3, correct? So let's try to calculate it. So I go into this general purpose register block. Register R0 is E5. Register R1 is 3, 4. Register R2 is 9F. Normally, these numbers would be taken from flash memory. And register R3 is 0x65, okay? And, you know, if you want, I can just, you know, I just erase the contents of other registers so they don't mess around. So let's try to calculate what the result should be. So the result should be, if we use calculator, so this number plus the second number is 13,541. The result should be 39,556, which is in binary. I'll try to just copy this number. I don't know if it's going to paste. Okay, so it worked. This, and this, which is in hexadecimal 0x9A84. 9A84. So, you know, the register R5 should be equal to 0x98, and register number R4 should be equal to 0x84, like this. So let's try to do it with our processor. So first we select, the result should be written to register R4. So I select write address 4. First register should be register 0. I set it to 0. Second register should be register 2. So B I set to 2. I enable writing. I select operation number 0, which is add. And now I just set clock rising edge, falling edge, and register number R4 already has the bottom part, which is calculated correctly, 84, right? It's right there. It should be that way. And now I just need to add the top parts. So for writing, I select register number 5. So it's register number 5. Is register number 1. I select 1. And register number 3 is the B register. And operation is also add. So I take clock rising edge, falling edge. It added the top parts, and I go into registers, and I see that the result is 99. So this is a wrong result, right? Because as you can see, when we added the bottom parts, we definitely had a carry out set because 1 plus 1 is 10, right? So there should be carry bit added on top of the R1 plus R3, because otherwise, if we add bottom parts, we actually have the risk of losing the carry. So for adding R5, we should have used operation R1 plus R3 plus carry, which is add with carry, which is actually instruction number 1. Okay, and where do we store this carry bit between additions? So we add bottom parts, and then we want to add the top parts and also add carry, because adding bottom parts in our case definitely produced carry bit. We store it in the status register. So if we, in our first examples, we only used very simple, one byte operations. But in this case, instead of addition, we should have used addition with carry. So let's try it once more. Oh, sorry, I also wrote down. So 9A, not 9.8, but 9A. So result is like this. So from calculator. So let's try again. So R0 is E5, R1 is 3,4, R2 is 9F, and R3 is 6,5. Now we want to add them together properly. If you want to, I can erase the contents of these two registers. So it's, we're at step 1. So let's try to do this, but in the proper way. So we add the bottom parts first, R0 plus R2. Result will be written in register number 4. Input, the first register is register 0. Second register is register number 2. Write is enable. Operation is add, simple add. And we do the clock going up and going down. Okay, and if we go into registers, we see that bottom part A4 is added correctly. And next, we also see that status register has some contents. It says number 5. Well, if we translate 5 to binary, it is 0, 1, 0, 1. So if we go into our arithmetic logic unit and check out which bit was which, we see that here signed overflow bit is 0, n bit negative bit is 1, 0 bit is 0 because the result is not equal to 0, and carry bit is set. So out of all of these flags, actually, we are interested only in this carry bit. Others are calculated, but we don't use them here. So carry bit is set, which means that carry bit is also saved in the status register so that its value is not lost between the instructions. So now when we do the second part, when we select that resulting register is register number 5, input 1 is register number 1, and input 2 is register number 3, and instead of addition, we select addition plus carry. So here we set operation number 1. When I do clock going up and going down, arithmetic logic unit took A, B, but also carry value from status register. It added all three of them together. And now the result, if I go in here, is the correct one, is 9A. Without the carry, it was 9, so it was missing 1 bit. So since we used, in our case, in this case, arithmetic logic unit automatically used the carry value from status register, it added the top parts of these 16-bit numbers together correctly. And you see that in register pair R5, R4, we have the correct value. R4 is 0x84 and R5 is 0x9a. And if we calculated it to decimal, it would be 39,556. Okay, so in our case, as far as we know right now, status register value is used in all of the operations in which we use carry. So we have add with carry 2 registers, subtract with carry 2 registers. So if we wanted to calculate the difference between pair R1, R0, and R2, R3, we would use subtract and subtract with carry for top parts. And also these bit shifts also use carry value from the status register. So logical shift left through carry and rotate left through carry and rotate right through carry. All of them use carry bit. Okay, so this is why we have this status register with carry. So I hope I answered your question. You asked me why do we need this status register, and we need it so that we can add bigger numbers than our processor can support in single action, so that we don't lose these bits between adding bottom parts and top parts. And the second reason why we have status register, right now it's not visible, but we will use it later. So status register has this carry bit, which we know how to use, but it also has other bits, for example, signed overflow, -0, and also carry bit. I'm gonna now go through all of them quickly. So V bit says whether we had signed overflow or not, right? So it's not very much used. Maybe you don't even have to worry about it. It is used in some software programs. But the negative bit, basically, if we're working with negative numbers, in all negative numbers in 2's complement form, the top bit is also the sign bit. If it's set, it means that the number is negative, and all positive numbers have top bit equal to 0. So by checking out the value of negative flag, we know whether the result was negative. For example, how would you realize in this processor a condition if A smaller than B, then do something. What you can do is you can just temporarily subtract B from A and store the result in some register, which you will not even use. But you can check if you calculated A minus B. If you calculate A minus B and negative bit is set, it means that the result is negative, which means that B is bigger than A. And you can, for example, and later we will do it, we will connect this negative bit cable to a special switch, which switches between what instruction do we do next. Do we do the next instruction, or do we jump to some place in the code? So these bits, negative and 0, are used to change the program flow, to jump between places, to perform this if. So for example, in another place, if I write, for example, if A equal to B, what it does is it subtracts A minus B. If they're equal, the result will be 0. The 0 flag will be set, and this signal will switch some big switch inside the processor, and it will switch to a different part of the program. We will do it, don't worry. But this is how we use these status register bits. One is to do the arithmetic functions for big numbers, and the second, we will use it later to switch between blocks of code in the program to perform these conditions. Okay, I hope I answered your question. And let's see, chat. Where is the chat? I don't see it. So this is not the chat. Ah, here it is. Okay, so your question has been answered. That's good. Okay, so next question that you might have. So I hope everybody understood that basically, you know, general purpose register, arithmetic logic unit, we select the inputs, we do the clock up and down, and the result is written to the register, and so on and so on. So next question that you might ask is, well, okay, this is very interesting, but how do we control these input signals? You know, is there a person that just manually switches these switches on and off by hand, or how does it happen? Where are these signals coming from? And actually the answer is pretty simple. Okay, these numbers actually come directly from flash memory. So when you open your computer, your favorite programming language environment, you type some code in, for example, C programming language. What happens is your code, I don't know, for example, you write C equals A plus B, you know. What happens is your compiler first translates this thing into assembly code, which would be, for example, ADD, which is the operation selection, basically, A, B, and, you know, write the result in C. But instead of A, B, and C, it will just use register numbers. So, for example, let's say A was located in register R0, B is located in register R1, and you want the result to be written in C, and it just happens so that C is located in register R5. So basically, your C programming code is compiled or translated into assembly language. This would be assembly code. And it is then translated into machine code. And machine code is basically the bits that are written in your program memory, in your hard drive. We just switch all these switches. And basically, so to add two numbers, operation select bits are 0, 0, 0, 0. So if it happens that these bits are located exactly in that position, then the machine code would just look like this: 0, 0, 0, 0 for operation select. Next three bits are, for example, for register A. So it's again 0, 0, 0, 0. Oh, in our case, just 3 bits, okay? Next, for example, next 3 bits determine the value of address B select switches, which is 0, 0, 1. Then 3 bits select address for writing. So we want the result to be written in register R5, so it's 101, for example. And then the next bit also determines the write enable. So since we want the result to be written into general purpose register, this bit is set to 1, for example. And basically, this is our machine code. So this code would be written in hard drive in the flash memory. And when you start up your computer, it just reads these instructions one by one. And just, these bits are basically connected to these control signals directly. And they just switch the state of this machine and perform the corresponding action. Okay. So machine code, program code, the binary is the one that controls the processor. It switches these bits, and in our previous example, for example, these two lines would, for example, in machine code, translate to addition is 0, 0, 0, 0, register R0 is 0, register 2 is 0, 1, 0, register 4 is 1, 0, 0, and write enable bit is 1. So I don't know, like this, for example. And the second line would translate to, for example, addition with carry is instruction number 0, 0, 0, 1. Register number 1 is 001, register number 3 is 011, and register number 5 is 101. And the write enable is also set, So this is how it would be translated into the bits that are written in hard drive. And when you execute the program, these bits are just directly connected to these control signals. Okay, did I just tell you something new that you didn't know? You can write it in the chat box, and also you can type in more questions right now in the chat box, telling if you understand what I'm talking about, or you didn't really understand. Or you can type in some questions if you have them. Where is the chat box? Okay, it's right here. Do you have some more questions? Okay, so I'll just keep talking. Of course, it's not exactly this simple, the translation, but it's approximately the same. So how to know which bit goes where in the machine code, you need to take the processor's instruction set manual. There is a special document, and in that document, it's basically written which bits in each instruction word are connected to which switch inside of the processor. Now, we could check out some examples. For example, there is this microcontroller called, for example, AVR is used in Atmel processors, Atmegas, which are used in Arduino. So for example, in microcontroller world, it's very popular. So AVR instruction set, there is special document, PDF, instruction set manual, and blah, blah, blah. There's some information, very interesting, but it also, I think, if I recall correctly, this document here, it says here's the operation. Each instruction is 16 bits long. And for example, destination register is located in the bits 0 to 4 because AVR architecture has 32 registers. Then obviously you need 5 bits to address each register. So, this is the machine code, which is consisting of ones and zeros, and the bottom 5 bits select one of the registers. Uh, register direct to registers. So here, if you have operation that works on 2 registers, then bits number 4 to 0 is one of the registers, and 5 to 9 is the second register selection. Then is something about input outputs. It has 64-bit input output direct addressing memory. Therefore, something like 6 bits are used to address that. Okay, this is too much information for you maybe. Now let's look at some practicalities about machine code. Let's say that the processor has 32 registers. It means that it will use, for example, to select between 3 registers, for example, to select register A, register B, and register for writing, it will need 5 plus 5 plus 5 equals 15 bits just to select between these 3 inputs. Then you have arithmetic logic unit. Well, okay, our arithmetic logic unit is very simple, basic, and it only supports 16 operations, right? Uh, I think this device supports 32. It doesn't have much more because, the more instructions you have, the more bits you need in the instruction word. But let's say, we have an advanced processor which has not 16, but 32 of ALU operations. So it adds another 5 bits in operation select in machine code, because each of these switches takes certain bits inside the machine code. And then we have other operations. For example, we have operation that says jump to a different part of the program. For example, if. So we need some kind of switch that switches between arithmetic operations and memory operations. And memory operations can be read from memory, write from memory, read from random access memory, write to random access memory, read from flash memory. So I just told you 5 options, and the 6th is arithmetic logic unit option. And then we also have conditional branch operations. So another 3 bits would select between ALU, memory, and branch instructions, for example. So in total, in this case, you have 23 bit opcodes, which is a lot of bits used to switch all of these bits. And actually, if I let you glimpse into a CPU that you will build, then, for example, here, there are even more control bits. For example, do you want to execute next instruction or jump to another? Do you want to jump to different places? Do you want to write to external memory or read from external memory? There are also instructions push and pop from stack. So the more functionality we have in processor, the longer these machine codes become. However, historically, memory has actually always been pretty expensive. So from a computer standpoint, we want these machine codes to be as short as possible. Therefore, in practically all microcontrollers that I can come up with, address for writing is actually the same as address of register A. This is the convention. You can like it, you can dislike it, but in most processors, the result is written in register A. And this is why oftentimes in instruction manuals, you would see, for example, our destination, then this arrow, our destination plus our source. So, which basically means destination is A and our S, source register is B. Actually, both of them are sources, but only one of them is also the destination. In this way, we just reduced our operation code by 5 bits. So it's just 10 bits to select between, for example, 32 registers. And here's 5. And these can actually be, some of these bytes can be reused in a very smart way, which we will also do in the labs. So generally, the microcontrollers tend to have 16-bit machine codes. Basically, all microcontrollers that are relatively cheap and simple, they have 16-bit machine codes. 8 is too little, 24 or 32 is pretty long, so all processors, if they can, they have 16-bit machine codes. Okay, so, you know, it's a compromise. 8 is too short. Memory is always built in 8-bit architecture, so 8 bits is too short, but 24 or 32 is too long, so 16 is what most processors use. So 16-bit machine codes. And in these 16 bits, you try to encode all possible combinations of these select bits. So since we're talking about memory, 16-bit machine codes are used, for example, in AVR. I think also in MSP 430 microcontrollers. So basically most microcontrollers. Even Windows, I think, used 16-bit machine codes for, older versions of, operating system, and these x86 processors, because we need to save memory. We can't just use an unlimited number of bits for memory. I think modern computers use still 32-bit machine codes. In computers and also in ARM microcontrollers. But actually, because memory is expensive, some ARM microcontrollers actually still use 16-bit long instructions. And let's look at what does it mean. So let's say you buy a microcontroller called Atmega 88. This second 8 means how many bits, how many kilobytes of flash memory this thing has. So Atmega 88 has 8 kilobytes of flash. But since you know that each instruction uses 16 bits to switch these switches, actually you can store only 4096 instructions. And if you select, for example, ARM Cortex M3 microcontroller, doesn't matter who is manufacturer, it's a standard. So ARM Cortex M3 microcontroller, this thing with 8 kilobytes of flash, this thing will only contain 2048 instructions, because it's ARM Cortex M3. It's the medium performance Cortex. It uses 32 bits for each instruction. So, oh wait, you thought you have 8 kilobytes, but no, you only have 2000 instructions that you can write into it, right? So, this is one of the reasons why Cortex processors are still, relatively more expensive. To contain the same code, they need 2 times more memory than these old 8-bit processors. Um, so, depending on the usage, you might want to still be using these old 8-bit processors. But where so where is the advantage of taking, for example, Cortex M3 processor? Let's say that you need to add two 32-bit numbers, 32A plus 32-bit number B. Now, if you want to do it on 8-bit processor, you need to do 4 additions in a row, because you need to add bottom parts, middle, and top parts. So it is 4 instructions. Each is 2 bytes times 2 is 8 bytes. 4 instructions, each is 8 bytes. Okay, so, but for example, ARM Cortex processor, it is 32-bit processor by design. So it only needs 1 instruction because its core is 32 bits. So 1 instruction is 4 bytes. It's just 4 bytes. So if you are working with big numbers, it's better to use a processor with big core, because then it can do the same thing with less instructions. But if you're working on small numbers, you're basically just wasting the memory. You might as well use just smaller microcontroller. Well, I don't know, maybe you'll only program web pages, so maybe this isn't really that important to you, but in some way this explains, for example, why 64-bit processors still use 32-bit numbers as their integer type, and why there are still 32-bit programs produced. Well, actually, after introducing 64-bit processors, it turned out that most programs don't really use 64-bit numbers. They're overkill, they're too big. So many programs are still actually running on the same 32 bits, and they don't really care. Because the more bits you have, the more memory you're wasting on, for example, storing very small numbers. So on one hand, the technology should advance forward. We should have 128-bit processors this year and 256-bit processors next year. But in reality, 32 is like really the maximum that we really need for most applications. And going over that only wastes memory. So that's where we are. And we have kind of like stopped at this level. So, and now this is about the flash memory, about operation codes. And as I'm showing you this example, for example, AVR processors, this is how the bits are organized inside instruction word. And I will publish this document for our microcontroller. And we will also have a documentation, even in a simple form of Excel document, which tells the locations of each bit. For example, in our processor, we will also have 16-bit long instruction words. And for example, first register will be selected by these 4 bits. So this is 4 bits, this is 4 bits, this is 4 bits, and this is 4 bits. Let's see, this is ID signals. So operation of arithmetic logic unit will be, for example, connected to these 4 bits. Since we have only 8 registers, we only use 3 select signals. So, this 4 bits in this place, the top bit will just be unused. This will be the second register, and this first part, we will do some encoding to control these write enable bit and so on. And so here we will have some other instructions as well. So some comparison instructions, loading numbers inside our registers, storing in RAM, jumping, branching, and so on. But generally, we will have 16-bit instruction words, and we will follow this documentation to implement them. This will be actually pretty easy. Okay, so this is that. And now, do you have some questions maybe? If you're interested, if you're going to program microcontrollers, if you want to, you can also check out, for example, ARM instruction set. And it's not really that simple. ARM has several versions. It has 64-bit, 32, and here is this thumb 32 instruction set. I think that this one is like reduced set, so it has smaller instructions, less bits. So I think Cortex M0 uses 16 bits for instruction because it's a little bit cheaper processor, so it has less bits per instruction, so it's simpler and also cheaper. Okay, so and finally, we will now talk a little bit about the memory and how the memory is connected to the processor. So this will be our CPU. Maybe you already know this, but it's in the program, so I need to tell you. So this is our processor. And as I mentioned before, we have some kind of program memory, like this, which just holds ones and zeros, the machine code. And it's just connected with 16 wires, one wire, one bit, to the CPU. And the instructions are just read one by one and fed into the CPU, and it performs the corresponding action. And CPU also has the second set of memory, which is random access memory, RAM. And so, for example, since the processor only has, 4, 8, 16, or 32 registers, but you can write long programs which have more variables. Of course, we need this random access memory where we store some values that don't fit into registers. And this construction is called Harvard architecture. And it just basically says, program memory is like a separate thing, and random access memory is a separate thing. And this is how most microcontrollers are built. This is a typical microcontroller architecture. For example, AVR. And I also think that PIC microcontrollers are also built the same way. So, this is how it's built. And the second architecture, which is more universal, is von Neumann architecture. And this architecture is what is used in the computers, and it is the following. So I'll just copy this part. And the idea here is to make the computer a little bit more universal. It has only one memory block, which is mixed program memory with machine code and random access memory. So this is how the computers are organized, because you turn on the computer, you initially don't know how much memory is used by instructions and how much the program will use for data. So it's just one big long chunk of memory, which is all basically is located in random access memory. So when you open the program, it copies the program memory from hard drive to random access memory. But from then on, the program just works with a chunk of random access memory, which runs the program and also stores the data. So you don't have to know how much RAM or program memory you need. It's just in one big long chunk. And if you need more random access memory, you just insert it into your motherboard. So this is kind of like more universal for bigger machines, for bigger systems. And the idea is that it's all in the same like area. And what this thing also allows is to run instructions from random access memory. For example, you want to do a firmware update, you cannot overwrite the machine code while reading it the same time. So what you can do is you can copy, for example, some updating program from program memory, just copy into random access memory, then jump to random access memory and run code from there, which, for example, erases the program memory and writes new program, for example, from other location, from, I don't know, from RAM or from UART or from USB. For example, the CPU has USB, it receives some information, it stores it temporarily in RAM and then copies to the program memory. And so you can, in this von Neumann architecture, you can update the program itself. In Harvard architecture, it's impossible. And usually these CPUs have a certain block of memory, which is called bootloader, which can do it, but it's not overwritten. So you can update the program, but you cannot update the bootloader. So if the bootloader has some error, then, well, you're just going to have to live with it. So this is the difference. However, this von Neumann architecture, you should take it with a grain of salt in microcontroller world. Because, for example, in CPUs, in computers, I would call it's a true architecture. It's just the way it is. However, in microcontrollers, for example, in ARM or in MSP 300, 430, etc., it's, cheating. So in these processors, in reality, even though program memory and random access memory virtually look like they're in the same field, program memory is, for example, at address 0, and it's all program, and then you have random access memory block, which is with the address that follows the last machine code address, for example, 0xFFA. I don't know, I just came up with this number. So in reality, random access memory is not the same as program memory, even though they are in the same virtual field and their addresses follow one another. In reality, random access memory is a separate piece of silicon inside the microcontroller. It is built in a different way than program memory. And you can write and read from RAM, but you cannot just randomly write into program memory. It's protected from writing. So in microcontrollers, yes, it's von Neumann architecture to be like more flexible, but in reality, it's physically built like Harvard architecture. Just from the CPU standpoint, it looks like von Neumann architecture. Okay, so this is the connection of CPU to memory. And maybe you have some questions about this. You probably already studied it. All computers, like computers, they are all von Neumann architecture, of course. I see that we're starting to run out of time. So I know if you don't have any more questions, then that's all of the information for today. And now a little bit about organization. I received some requests from you that maybe it's possible to have the lab in person in school. So how about this? If you want, you can do the lab at home on your personal computer and don't go to school. But for example, if you want to go to school, then I will be in this room 418. And if you want, you can go to school, you can ask me some questions, you can do it in the school. But if you don't want to, you can just sit at home and do it at home. So I will be at school tomorrow. For example, we have lab, I think from 12 to 2. um, I will be there. If you want, you can come. If you don't want, you can do the lab at home. I put the materials for lab in Artus, so you can just go through the videos that show how to do the lab. You do it, you save your file, and you upload it to Artus. And I'll just open it. I'll see that you have uploaded it, that you have done it. So it will be a credit for the lab. And if you want, you can go to school to do it, but you still have to upload the progress in Artus so that I can put you some marks later. Okay. And when I'm at school, I will turn on Zoom also. So if you want to ask a question, you can type it in the Zoom chat box. And then, if I have some free time between students that are at school in person, then I'll just either write the answer in the chat box, or we can talk over Zoom if you want to. So I think last time, when it was a week ago, some people connected to Zoom and actually asked me some questions. So, you can do it if you want to. So the lab tasks are in Artus. You can just go there, do them, and we're basically working in the same file. We're just updating and updating our microcontroller until at the end of semester, you will be shocked at what you will have built. Okay, so if you don't have any more questions or comments, then you can just disconnect from this Zoom thing. So if you want to do the work at home, then of course you need to install Logisim on your computer. But you need to install this Java runtime environment, and then you download the Logisim from the internet. And important information for you, please, when you work in this Logisim thing, please save your work from time to time, because last time there was this one boy in our Latvian group, and he made everything, and at the last step something there was some bug with the computer or something, and basically he lost all of his work. He had to do everything again from the beginning. Don't be that guy. Be smart and save your work from time to time. Okay, so if no more questions, then I maybe see you tomorrow, maybe I don't. You choose.